Scientific approach to knowledge. So scientists have a specific way they approach actually all of life. I find myself solving problems at home using the scientific method. The scientific method is a general process. So we observe nature and how it behaves, and we make observations, and we do experiments to test those ideas, and then we draw conclusions from that. So the key characteristics include observation, formulation of hypotheses, experimentation, and finally the formulation of laws and theories. We'll talk about each of those. Observations are also known as data. Descriptions about the characteristics or behavior of nature. They just find a place to hang out. Actually, here's a chair. Data can be numbers, the mass of an object, the temperature, or it can be a descriptive, qualitative. What color is it? How hard is it? Those sorts of things. So as an example, this is the example given in your book. Antoine Lavoisier, famous scientist that lived in the 1700s. He made careful measurements of the mass of objects before and after burning them in closed containers. So people don't usually do that. Usually you burn something in an open, like a fireplace or something. But he was curious about burning, and so he burned things in closed containers, measured the mass before and after. His observation was that there was no change in the total mass of the material. This doesn't happen in an open container, though, right? If we put a big log, maybe it weighs 5 pounds, you put a log in the fireplace and you burn it, does it weigh the same 5 pounds afterwards? No, it's reduced to a little pile of ashes that weigh almost nothing. So by doing this in a closed container, he came up with a different result, and he made an observation about that. So the observation often leads to a hypothesis. So the scientist observes these things, and then we want to know why. Well, many of these things, there's nobody, especially back in the 1700s, nobody could explain this to him. Nobody knew why this was happening. So a scientist tries to think of why this could be happening. Come up with a hypothesis. Hypothesis is a tentative interpretation or explanation. It's not really a guess because you think about it more than just wildly guessing at something. But you try to come up with an explanation that makes sense to you. So Lavoisier said, well, I think that when a substance burns, it's combining with some component of the air. And that's why the mass doesn't change. Because obviously the mass of the ashes is less, but overall the mass is the same. A characteristic of a good hypothesis is that it is falsifiable. So when you make a hypothesis, it needs to be something that you could test and possibly prove wrong. If you hypothesize that invisible Martians came in and did magic inside the closed container, could you prove that wrong or right? No, because invisible Martians doing magic, that's just like, how do you even test that? So that would not be a good hypothesis. After we have the hypothesis, we test the hypothesis using an experiment. An experiment is a highly controlled procedure. There are things called variables. The temperature, the amount of light, all kinds of different things, and we try to control the variables. We try to control all the different things and do this procedure, this experiment, to see if what we theorize is correct. The results of the experiment may support the hypothesis or it may prove it wrong. What do you do if your hypothesis is wrong? You quit and go home? No. You either modify your hypothesis, kind of tweak it, or you say, well, that was like just totally off base, let's come up with a new one. And you keep going. Scientists fail a lot. We try stuff, it doesn't work. You try stuff, it doesn't work. You try stuff, it doesn't work. You keep doing it, and eventually something's going to work. My graduate research felt like banging my head against a brick wall. Eventually I got enough that they let me out. But, yeah. So after the experimentation, ultimately is the formulation of laws and theories. And it's important to understand the difference between laws and theories. A scientific law is a brief statement that summarizes past observations and predicts future ones. A law says what happens. If I do this, then this will happen. So, law of gravity, right? If I hold this dry erase marker out and let go of it, what's going to happen? It's going to fall to the floor. Yep, every single time. Does the law of gravity explain why this happens? No, it doesn't. So the law just says what happens. An example, the law that came out of Lavoisier's experiments is the law of conservation of mass. It says in a chemical reaction, matter is neither created nor destroyed. That was an important concept. Matter can be rearranged, the atoms can be formulated differently, but they don't appear or disappear. The mass stays the same. Scientific laws are also subject to experimentation. It is possible to prove a scientific law to be wrong. And unlike laws made by the government, you can't choose to violate a scientific law, a natural law. You can't say, well, I am not going to obey the law of gravity today, and I'm just going to walk off the edge of the cliff. It's not going to work unless you're Bugs Bunny. It's not going to work. You can't just choose to disobey, like we can choose to disobey the speed limit, right? So, scientific laws describe how nature behaves. The theory is explaining why. So, it's a model for the way nature is and tries to explain not merely what it does, but why. So, law says what happens, theory tries to explain why. We get a theory from one or more well-established hypotheses. So people have a hypothesis, and then it's tested and tested and tested and tested, and there's no like magic point where it suddenly becomes a theory, but eventually it may become a theory. So John Dalton's atomic theory was devised to explain the law of conservation of mass. He proposed that matter is composed of small indestructible particles called atoms. And because these particles are merely rearranged during a chemical change, the total amount of mass remains the same. So you can imagine taking some Lego bricks and you made a little house. And you're going to take the house apart and make a car and a tree. Or make two other things out of it. Does the mass of the Lego blocks change? No. It's the same pieces. You just took them apart and put them back together. And that's what's happening in a chemical reaction. We're taking the atoms apart and putting them back together in a different way. And so the mass cannot change. Theories are also validated by experiments. One of the things that's sometimes disturbing to students is that in science, you cannot prove anything to be true. We can't prove that it's true. We can only prove things to be untrue. We can prove things to be wrong. And so a theory is whatever we currently believe to be true, no one has been able to disprove it yet. Sometimes new developments come along in technology where a theory can be disproved. More often, it just needs to be slightly modified. We can use theories to predict what's going to happen in the future, and so they get very, very useful. Sometimes, in everyday life, oh, well, that's just a theory, right? In science, it's not just a theory. A theory is a big deal. A theory is as close to truth as we get in science. So here's sort of a flow chart. Sometimes people think that doing science is a specific set of rules, like following directions on building a Lego set or something. You do this, you do this, you do this, and you get a result. That's not how it is. It's very messy and circular. And so we'll often go around and around and around before we find anything awesome. So we have observations, and those can come about intentionally or unintentionally. From the observation, you develop a hypothesis. The hypothesis needs to be tested by experiment. The experiment may confirm or cause a revision in the hypothesis, or it may cause you to just throw it out and start over again. And so you can go around and around in here modifying your hypothesis for a very long time, a lifetime, actually. Observations also lead to laws, but those need to be tested and confirmed again by experiment. Hypotheses can lead to theories, and then theories are also go around and around here and get tested. Scientists tend to be pretty skeptical about things, and somebody will publish their research in a paper and say, this is how it is. And other scientists read that and say, I'm not so sure. I want to try it for myself. I'm going to see if I can find something wrong with what this other guy did. And so we publish articles with our research, and then other people, we actually tell exactly how we did it so that other people can try it as well. And if it was a good experiment, other people are going to be able to replicate those results in their lab. But by publishing it, you get credit for it if you're the first one to publish it. So which of these statements best explains the difference between a law and a theory? A law is truth, whereas a theory is mere speculation. B, a law summarizes a set of related observations. A theory gives the underlying reasons for them. C, a theory describes what nature does. A law describes why nature does it. What do you think? Everybody's going to be shy. It's C. No, it isn't. It's B. This one's appealing because if we switched what and why, it would be correct, right? A theory describes why nature does what it does. A law describes what. So there will be multiple choice questions on my exams. And there are some things that I'll try to trick you with. And so you got to read those questions carefully. Any questions?